All right, just a few things back to PT graphs. And even though we're going to be moving on to VT graphs today, velocity time graphs, we're going to kind of like cross-reference PT graphs at the same time. Because one skill that's going to be important in the future, especially in labs, is if you see a PT graph, once we go over this next stuff, you should be able to predict what the corresponding VT graph for the same time interval looks like, or vice versa. I could give you a VT graph, and you could predict from that what the PT graph might look like. There is a such thing as acceleration time graphs. However, we don't really bother with them in this level because since we're stuck in algebra, algebra-based physics, there's nothing too fancy that goes along with acceleration time graphs. They're always like flat lines on some uniform acceleration. Those would be studied more probably in a calc-based one, okay? But anyways, before we move forward, let's go back to some general features. I'm just going to roughly draw. You don't have to write any of this, just pay attention and answer some of the questions I got. I'm going to roughly draw some PT graphs for the X and Y axis. Remember, for these things, we never draw a second or third quadrant because time can't go backwards, but positions on this axis, times on this axis. Position will most typically be in meters, time in seconds. I don't care about exact values right now, but if I gave you a PT graph that looked like this, what could you say about the motion of that object? It's not moving. Good. Whatever position that is, whatever number that is, it's staying steady at it, right? So as time moves on, its position is not changing. What if I did one that looked like this? Chris? Nope. Be careful. It's going, if it's linear, it's some kind of constant velocity. And what kind of slope does this linear graph have in general? Go ahead. Negative slope. So the best we could say about this one is that we're moving constant in the negative direction. All right? Constant negative velocity, in other words, okay? And then obviously one like this would mean what? Go ahead. I'll give you the positive direction, but we can't say speeding up. Constant. It's linear. On PT graphs, linear means constant velocity, okay? So if it were speeding up, though, what general kind of shape would it have to have? Chris? Right, some kind of curve, right? Usually, unless it turns the whole way around, which we'll get to, but assuming it doesn't, then it's got to be some kind of partial parabola, all right? There's two general types of parabolas that could represent speeding up that we ran into on that worksheet if you watch the video. One that might look like, doesn't matter really where on the graph that occurs, the shape is what matters. So this would be an example of speeding up. Notice as time goes on, the steepness of it increases, right? This one in particular would represent speeding up in the positive direction. But just be careful. I know it's in a negative positions all down in this quadrant, but it's still, even though they have negative positions, this object is still speeding up towards the positive, right? Right? It's going towards positive, so that makes it a speeding up acceleration in the positive direction. If we were speeding up in the negative direction, it would have to get more steep, but it would get more steep going downward. Both of those represent the two ways to speed up. All right? This one's speeding up in the negative direction, speeding up in the positive direction. So if a curve that gets steeper represents speeding up, what would the curve have to do to represent slowing down? Yeah. Right, instead of getting steeper, getting less steep, right? So this would be an example of one that is flattening off, right? So that's going in the positive direction, though, sweeping upward, right? Upwards positive. That would mean slowing down in the positive direction, getting less steep. And slowing down in the negative direction, something like that, right? Getting less steep. So that's pretty much every option we have right now for 1D kinematics, other than one. What if we did have a full parabola? What if we did have something like this? It was mentioned yesterday in the video near the end. Go ahead, Chris. You're right, except for one big feature, Reese. The change in direction. Because the first half, if we split this parabola up into two halves, you were right. We slowed down, and mathy term here, the vertex, right? The vertex for a moment, we have to stop, then we change direction, didn't we? All right, so this would represent like going one way, like that's a positive direction, okay? This started from the origin. Let's say right here's the origin. This would represent me going this way and slowing down, stopping for a moment at the vertex and then speeding back up in the negative direction. Make sense? And we could flip that, the direction of it around, and we could have a parabola that does that, which is the same idea, just flip-flops the direction, but you're still slowing down, then speeding up. So anytime there's a full change of direction on an axis, then you have a full parabola. If you're just speeding up to a certain point or slowing down to a certain point without turning around, then it's going to be a partial parabola. Make sense? Question? Well, since we're going up with one object, we can only have one graph, but it can't have different segments. So this would mean slowing down in the negative direction. We could have several segments. There was a couple parts on the study guide that had like two segmented things, and we described what it was if you watched it. So let's say we slowed down where we completely stopped. If we completely stopped for whatever amount of time, it would completely flatten off. So this would be like, I'll put a dot at the different segments. So that's like, then maybe we speed back up, right? Maybe we speed back up if we speed back up in the negative direction, we would go like this, right? Because it gets steeper. So that kind of motion, can definitely happen. It can occur. Usually, once we start applying equations to this stuff a lot, very soon, we'll do it like segment by segment, all right? Not as a whole thing. Once things start to change, then this isn't one whole function right here. This is a function where you can take pieces of it and mathematically fit it here, here, and here. So when we change something about the motion, we lead into a different segment, and then we'll treat it almost like a separate problem, but we could put it all together in the end. If that makes sense. All right. You'll see us do stuff like that later. Does that answer your question? Okay. All right. So that's pretty much the gist of most stuff from yesterday. One of the last thing was you had some linear steady ones at the end, where if we physically have numbers on here and can calculate the slope, what does the slope represent? Yes. Change in position over time, which is the same as displacement over time, or otherwise isn't that velocity, right? That's one of the biggest things about all this stuff. When we take the slope of a PT graph, when we take its slope, the result is V equals d over t, because displacement is a change in position. And x-axis is time, so it is divided by the time it took, right? So that old equation from a week or so ago, I told you someday we were going to prove mathematically where it came from. It comes from the slope of this graph. And one last little thing, remember I said we don't do calc in this class. It's not a calc-based course. But I do want us to understand something that was kind of mentioned at some point. So what if we had one of these speeding up curved graphs, right, on a PT graph? If we let me make a better curve than that even. Let's say I have a curve like this. Real defined curve. Let's say I tried to take slope on this graph. All right, just like I did a linear one, but this is obviously nonlinear, right? So I'm going to put what we would need, 2 points, right? Minimum of 2 points to take slope. Now I could still take the slope of this, right? But would it be very accurate? No, because what the math will do, change in y over change in x, or in other words, more particularly, change in position over change in t. Doing the y2 minus y1 over x2 minus x1 thing. It would think, the math would think that the line didn't curve. It would think that it went through those points linearly, right? This is why we said with that formula v equals d over t, that at best, this is what value, unless you know it's going constant. At best, this is what kind of value? Not in this case. Yes. An average value. All right? So if this thing did speed up or slow down, I could still apply v equals d over t, but it's not instantaneous at any given moment, is it? It's an average between those points because the line's curved. Does that make sense to everybody? This is why algebra limits us. Because I'm not going to teach you calculus, but I'll teach you an really important idea behind it that's really easy if you get this right now. What calculus does is say, well, let's make a play on this. Take some of this stuff off. These 2 points we have, what if we got the pick 2 closer together points? Like here and here. We'd have the same problem. There's still a curve between them, right? It would still be an average, but aren't we zeroing in closer to a more defined part of the curve if we bring the points closer? Well, what if I bring them closer again? What if I bring them for eternity closer and closer? All right, that's called a limit. Have you ever heard of that? How many are in calc right now? Any of you? No, you're all juniors. You wouldn't be. All right, this is a simple idea. Once you put the real math to it, it can get difficult. But the idea is simple. Let's say we bring 2 points closer and closer together. I'll give you a concrete example. Imagine that I tell you I'm going to give you some rules. I'm going to walk to that wall. Every move I make's got to be halfway to it. All right? So my first motion, I go halfway to the wall. My second motion, I go another halfway to the wall. My next motion, I go halfway to the wall. Halfway to the wall. What, if I do that forever, will I ever touch the wall? No. Because halfway of some real number is never going to be what number? Half of some real number will never be what? 0, right? So if for eternity I approached that wall halfway, I would never meet it. But if I even did it for a little bit of time in front of you guys, I would eventually get so darn close that it would seem to you guys like I'm touching it, right? I'd get so close. If I went to it for eternity, that gap would infinitesimally get smaller and smaller and smaller. It's the theory of a limit in math, okay? We imagine the same thing with these 2 points. What if for forever I keep cutting the gap between them halfway? Would they ever really be the same point? No. But at some point, very quickly, as we say the limit approaches infinity, that's how it's said in math, that they will get so darn close together, they might as well be the same point, because you couldn't even tell, right? Make sense? So that's what the play that calculus makes on algebra. We're still technically using 2 points to get slope in calculus, but we bring them so close together, it basically like it gets blurred and they might as well be 1 point. The gap between them, which is the curve on this thing, is so darn small, this is actually now better than average. Does that make a little bit of sense? It's so darn small that now this slope to be drawn like that is only touching this curve at that real small spot. So that's why you need calculus to eventually do this stuff more accurately mathematically when we have curves involved on the graphs. There's a lot more to say than that, but that's kind of the start of everything. Okay? That's actually ended up being called a derivative, which is one of the cornerstones of early calculus. All right, but you don't have to know that. You have to know that if we use 2 points on a curve, at best it's an average, right? To find the slope. And that's average velocity v equals d over t. But if we use it on a linear line, that's better than average, right? Because that linear line does go right through them. So that linear line means it's going constant velocity, so therefore if we use v equals d over t, it is instantaneous velocity at any moment, not just an average. Yes? Yeah. Well, as long as it's a smooth curve, a single parabola, you don't need many equations because one will make it, okay? Or at least part of one bound on a certain range of x values, okay? Does that kind of make sense? If the curve changed its pattern, maybe we'd have to put a new function on where it changed. But as long as this is a true parabola, one function could describe that to infinity. But usually, typically with us, we're not looking at stuff to infinity anyway. We're looking at this in a not just a general math sense. We're applying this to something that traveled for 5 seconds, 10 seconds, some defined interval. So we don't even really worry about what our application of it, how like going on forever or something like that. In general math, of course it does. That's why we draw the arrows at the end, right? Okay. So that's some recap of stuff from yesterday to remember and still consider as we move on today. So I'm going to go back to the moving man simulation. And we're going to look at first VT graphs alone, then we'll kind of look at both at once. Now here's the thing. These are actually technically, the VT graphs are going to be even simpler than the PT graphs. But here's where it's going to gets probably difficult for some students. They get them confused. Certain features on a PT graph that visually look the same on a VT graph mean something else because it's not a PT graph anymore. It's a velocity on the y-axis versus time graph. So we can't get these simple things confused, okay? So let me bring this guy back up. I'm going to set a velocity, just a small one, at 2 meters per second. I'm going to get rid of this graph and this one for right now. When I hit play, this is going to send this guy off at a positive 2 meters per second. Constant, okay? The acceleration, I let it 0 for now. So, if I hit play right now, let's predict what kind of graph would this make. Remember, this is a velocity on this axis now. It's no longer position. Time is still on this axis. This is velocity. So when I hit play, he's immediately traveling it. I set it at 2 meters per second. What will my graph maybe look like before I hit play? Look at that. It will be linear, but I need it more specific. There's. You're overthinking it. Right, now remember, this is velocity, right, if this axis. So if velocity stays constant, won't it be a flat line? This is no longer position on this one. So if I hit play, and this guy's already in motion at that 2 meters per second, let's go for like 4 seconds or however long. Right there, I'll pause it. So, see here's 0 velocity, right? Right there's 6, so there's about 2, right? It stayed steady at 2 meters per second, right? So that tells us something. All VT graphs, always, 100% of the time, if we have no acceleration, if we're just constantly traveling at a nice steady velocity, it will always be flat, won't it? Now here's where we got to be careful. What did we say flat meant on a PT graph? Yeah. Nope. No, you're not moving at all. Flat on a PT graph. So this is what I mean. You got to keep it straight between the two. Remember what's on what axis. Flat on this graph means constant velocity. Flat. Not just linear. Linear flat. Flat on a PT graph meant you were stopped and holding your position steady because that's what's on the y-axis. Does that make sense? All right, so you'll just have to get this stuff straight. Now I'm going to reset this. Well, let's see what stop looks like on this one. So I'm going to just let everything stop. And just hit play. He's not going to move. It's flat again, but remember, being stopped is a constant velocity of how much, guys? 0. So stopped on a VT graph will always be flat at the origin. Stopped on a PT graph could be at the origin, but it could be somewhere else because you could stop at different positions, right? So, but for a VT graph, stopped will always be on 0. I'm steadily staying at 0 velocity, right? 0 meters per second. Make sense? Okay. Now the next part, putting in an acceleration. Now this again is where, in this course, we only study uniform accelerations. I'm going to have this guy start from rest, but if he starts from rest, 0, if I hit play and didn't put any acceleration, it would be what I just did. It would just be flat. He wouldn't go anywhere, right? I'm going to start from 0, but give him an acceleration of 1 meter per second squared. So he's going to speed up, all right? The question to think about, you don't have to say it out loud, just think about it to yourself right now. What's going to happen when I hit play here? All right? He's starting from rest. I have an acceleration that's going to cause him to speed up. It is a positive acceleration, so therefore he should go to the right. And when I hit play, let's watch what happens. And now I have the position one up because I want to kind of cross-reference it with it, okay? Notice this one's curved, right? Just as we said, the old PT graph from the last couple of days, a positive acceleration, it's getting steeper as time goes on, right? But the velocity time graph stayed linear, didn't it? And that's what will happen. As long as the acceleration is uniform. As long as the acceleration rate stays the same. I set it at 1, it stayed at 1. That means every second that goes by, remember, 1 meters per second squared, right? Every second that goes by, I speed up by 1 meter per second. That's a nice pattern, isn't it? That's a consistent pattern with velocity, which is why velocity is linear. Does that make sense? Velocity is linear, but if we go back to the curve, a curve also means like kind of somewhat of obviously non-linear, but one thing is growing faster than the other when you're doing that. But on a straight velocity scale, a nice uniform acceleration, if my acceleration was 3 meters per second squared, every second my velocity is increasing by the same amount, right? 3. That's why it's linear. Okay? So it's pretty simple. If I have a positive acceleration, I will always have a sloped line, linear line with a positive slope. Okay? If I change my acceleration to negative, let's reset. I'll still start from rest. If I change my acceleration to negative 3, there's that graph and focus on these ones, hit play, I go and I speed up in the negative direction. This graph's showing me that from before, right? It's dipping negative, getting steeper this way, but this is showing the VT graph implies the acceleration. And the acceleration is making me get faster in the negative direction, right? This goes from 0 to down here, I'm a little bit past negative 6. But the magnitude is what matters the most here. 6 meters per second is my speed just in the negative direction with the sign on it there. Right? But that slope is the acceleration. So get this straight. This is super important. You remember yesterday when we took the slope of a line on this graph, that was velocity, right? V equals d over t. We gave you, more than a week ago, the acceleration formula. A equals vf minus vi over t. We had to use it on the quiz, right? Final velocity minus initial velocity over time. Guess where that came from? Not out of thin air. Look at this. This axis is v, right? This, where I ended right here, whatever that number would match up to be, that's my final velocity at the end of the interval, right? My vi was 0 for this case. I started initially from rest, right? It took just over 2 seconds. So if I took the change in the y-axis, which is actually v, so change in v over the t, the time it took, that is the formula we already gave you. So this one proves that its slope is the acceleration formula. This slope is the velocity formula. That's probably the most important thing mathematically to take from this, other than the trends of the graph. Because we have uniform acceleration, you will never, ever get a curve on a VT graph in this class. Okay? We don't study anything beyond uniform acceleration. So put it this way. If you were in your vehicle and somebody was plotting your graph and you were doing this with your gas pedal, you'd be going like this, right? And there's actually a name for that. It's like, we would even just call it like jerky motion, right? It's actually physically called the jerk. Right? But it takes calculus to do that, and you get crazy curves all over the place. And then slopes don't do anything for it. And that's when you get into kind of what I was talking about there. Okay? So I'm not saying you can't have curves on VT graph. You're just not in this course, okay? So that's going to simplify for you. There's really only 3 general styles of graphs a VT can make. This, if it's flat, that means the VT graph has 0 acceleration. It's staying steady at some constant velocity. Right? Like this, positive velocity, positive acceleration, I'm sorry, because the slope of it. Positive acceleration because it has a positive slope. Like this, negative acceleration. Right? I'm going to start the guy to do some variations of this. Actually, let me do a few other things first. Let me reset them. Let me again give him 0 acceleration. And just because we didn't look at both graphs with us. Let's go constant velocity again. I'll go constant at 4 meters per second. 0 acceleration. So let's see if we can predict both graphs. No acceleration, the velocity graph should be flat. Right? He stays steady at whatever velocity I set him at. Position, since he's not accelerating, there won't be a curve, will there? if he goes in the positive direction, the position one should be linear this way. So when I hit play, there it is. That kind of makes sense? It'll take a little while till you really have it hitting, but those are the ideas we got to use. If I gave him a negative velocity, I'll just continue on. There'll be a second segment. And hit play. He turns around. Still steady, no acceleration, but now he's going in a negative velocity. See how the graph dropped down to here? All right, very quickly. And then this one turned around, right? Now let me ask you this. I'm going to flip back to here. We just talked about earlier, reviewed the fact that turning around on a PT graph, you have to have a full parabola, right? Well, how would we represent turning around on a VT graph, guys? Remember what I just said, VT graphs for us aren't going to do what? Curve. So if it can't curve, how could we represent turning around on a VT graph, Ferris? What's that? It can be, but I'm looking for a key piece of information. Yeah. Not quite. Let me give you a little hint here. On the y-axis, all the values up here are positive. Of course, that's the origin. This is negative. Reese? Yes, exactly. This is the origin is the boundary between the directions of positive velocity and negative velocity. So if I had a line like this, remember they could only be linear on these if we're doing uniform acceleration, right? Now, that line, the couple of things we could tell from it, it has a positive slope, right? It has a positive acceleration, that means. But it crossed over. So what this shows me, I'll make the guy do it in a second. I started with a negative velocity, but I'm going to zero. If I'm approaching zero velocity, what am I doing? Speeding up or slowing down? If I'm approaching zero velocity, I'm getting closer to it as this line goes on. So I'm doing what? Slowing down. So for this segment of the graph, from here to here, I'm slowing down, right? Right when I touch the axis, if I go through it, for a moment I have to do what? Stop, because I go through zero, right? Zero velocity means I have to stop. But then I cross over into the positive velocities, right? So that must mean I turned around, right? And once I cross over, I'm getting further away from zero, not closer. So am I speeding up or slowing down in this part? Speeding up. So even though this is one uniform acceleration, it has different things the guy's doing based on which way he's going, isn't it? The acceleration's the same the whole time, because if I found the slope of that, that's a linear line. It stays the same the whole time, right? But this should correspond with something else we already learned. Everything starts falling into place now. Remember we said a negative acceleration, or let's put it this way, a positive acceleration doesn't have to mean speeding up, does it? Nor does a negative acceleration have to mean slowing down. It's all about what the sign of your V is at the time it's happening. Isn't that what we're looking at here? During all these times down here, my V's are what? Negative. But the whole time my A, because of the slope, is positive. Didn't we always say if V's are negative and A's is positive at any given time, we're slowing down because they're opposite signs? This is just proof behind that. Better than just a statement now. This is the graphical, mathematical proof behind that. And then up here, all these, anywhere plots for my V's on the y-axis, all these are positive, right? And my acceleration is still positive because that's still a positive slope. Positive means you're doing what? Speeding up, right? We could do a similar thing if we drew a line going this way, just flipping the idea around. If it went like that way, we have a negative slope now, right? That means a negative acceleration from the VT graph. But up here, we have positive values of V, right? So we're going slower, and we can see that graph because we're getting closer to zero, right? We still have a negative acceleration down here, but since we have negative V's as well, now we stop, turned around, and they're going in, getting faster in the negative direction. My numbers will be getting bigger in magnitude down here, in size. They're negative. That just means direction. Does that make sense to everybody? Yeah. I'll show you with the guy how to make one of those and what he would do and how it would correspond to the position graphs as well, okay? Hopefully that'll help. just want to go over the idea first. So I'm going to give this guy, I'm going to start him not at the origin. I'm going to start him at some positive value. I'm going to clear the ground. Stop. I'm going to give him a negative velocity, say like -8, okay? Notice his position is not the origin, it's just close to 6, right? Now, I want him, if I just left it as is, he would just start going this way, right? 0 acceleration, he would just stay steady this way. What I want him to do is turn around eventually and come back. So he's going to start going this way because of the -8 for velocity, and that's the negative direction, right? If I want him to eventually turn around and even come back, what sign will I need on a non-zero acceleration? Positive, all right? Because he'll have to slow down and then turn around and speed up in the other direction, and that should be what I'm talking about. So let me give him an acceleration of +2. Close the acceleration graph. Watch both of these. It should be what we just talked about. Watch the VT graph especially. Gonna slow down. Don't hit the wall. Don't hit the wall. Don't hit the wall. Turn around. You hit the wall. I gotta do it. I gotta set the original one. Hold on. Hold on. Let me clear that. Stop it. Hold on. Let me go back. Clear. Let me set this at -6. I had it going too fast. You hit the wall. But my A should still be at, A is going to be +2 again. Let's play it again. Stop for a moment, backtracks. And now look at both of those. Like we just said, a turnaround means it has to stay linear on a VT graph, right? So it has to cross here. We started with the negative velocity. That's what I just gave him initially. But right away, he had a positive acceleration causing him to slow down or approach 0 here, right? But once he stopped, remember, what causes accelerations? Forces, right? So whatever force made him, his feet, whatever, in this case, that gave him the acceleration, he continued it, and it turned him around. He didn't just stop, it turned him around because the acceleration continued and came up and turned around, and now we're speeding up in the positive direction. And cross-referencing it with the corresponding position time graph, the position time graph did what we would expect, like we talked about before, right? If he turned around, that means we got a full parabola, right? And that parabola became less steep to the point where he stopped at the vertex, and then he got faster, so it became more steep, right? So we'll go through these scenarios more on the worksheet tomorrow, but that's all the main ideas right there. And just let me stress one more time that if we took the slope of this, if I took this point here and this point here and calculated its slope, that tells me what exact value? The acceleration. That's the formula for A equals VF minus VI over T. All right? I'll stop right there. We're almost out of time anyway.